Hi, I'm Yingying. Welcome to another Bifrost tutorial. Our topic today is looping. In the loop, the same process is repeated at each iteration. Being able to construct loops allows you to rapidly generate a large amount of data and create shapes with a high level of complexity. In this tutorial, I'll first introduce the looping constructs in Bifrost, including auto looping, for each, iterate, and do while. Then I'll show you how to generate colors and create this animation using a combination of loops. Without further ado, let's get started. Here I have a sequence array of 10 zeros. For displaying the data, I use the print pack developed by my colleague Roland Ryer. It's super helpful in outputting values, displaying arrays, and labeling points. I've included the link to Roland's print pack in the description. Now I use this sequence array as the input of the loops that we're going to construct. Let's start with auto looping. Say I want to add the same number to each element of this array. I can just get an add node and create a value node. Enter 5 here, and we see that the output array has 10 5s. If we zoom in, we see these 3 arrows and dot symbol on the port where the input array is connected, which indicates that the node has been auto-looped, meaning that it takes each number of the input array and adds this value to it. In an auto-loop, the same operation is applied in parallel to every element in the input array. If we change this added value, we see that all the elements in the output array update accordingly. Similar to auto looping, for each is also a parallel loop. In many cases, we use for each when we need to use the iteration counter. For example, if we want to add to each number the square of its index, we can use a for each loop. Connect the array to it. Most of the time, we don't need this max iterations for constructing a for each loop, so let's delete it. Go inside the compound, right-click, and set the port iteration target to true. We can see from this icon that the port type has changed from an array to a single value, meaning that this loop will now iterate over the sequence array. And for each index, it will get the corresponding value. To add the square of the index to each value, get the power node, connect the current index to base, and set the exponent to 2. Then add it to the value of the input array. Connect the result to the output, and we get the new array. If we change the input array, the entire output array will update automatically. Auto looping and for each are very efficient because they can process a large amount of data in parallel, taking advantage of all the cores on your machine. But there are situations where we can't loop in parallel. For instance, if we need to use the result from the previous iteration, then we must do it sequentially. In this case, we can use the compound iterate. An example would be to create a Fibonacci sequence, where the first 2 numbers are 0 and 1, and from the third one on, each number equals the sum of the previous 2 numbers. Let's see how to construct it. Connect the sequence array to the iterate compound, and connect the size of the array to max iterations, so that it will iterate over the entire array. Go inside, and we need to set the sequence as a state, which gets updated for every iteration. Here's how we do it. Connect the sequence to the output. I'm going to rename it out sequence. Right-click under Set Port State, select Sequence. Now we see that the ports for both the output and input sequences have the same circular icon. This means the output sequence from one iteration will become the input sequence for the next iteration. And this way the array will keep getting updated until the end of the loop. Now we're ready to tell it what to do for each iteration. Let's get an if node to set the condition. If the index is less than 2, we set the number to be the current index of the array. If it's greater than or equal to 2, we set the number to be the sum of the previous two numbers, which we can retrieve using the getFromArray node. And the index should be the current index minus 1 and that minus 2, respectively. Connect the result to our sequence and we have the Fibonacci sequence. Let's combine these into a compound so that we see the structure of the iterate construct more clearly. Here it updates the sequence and sends it to the output. This updated sequence will become the input sequence for the next iteration. If I connect the value node to the max iteration and gradually increase the number of iterations, you'll see the update after each iteration. A do while loop operates under a condition. Once the condition isn't satisfied, it would exit the loop. For example, the same Fibonacci sequence, if I want to stop it when the number is greater than 8, I can use a do while loop to set the condition. Let's copy and paste the Fibonacci compound into the do while loop. Connect the sequence and current index to it. And set the port state to sequence, just like what we did in the iterate compound. Here in the output node, we see this port looping condition. It takes a Boolean value. When the value is true, it keeps looping. When it's false, it will execute for one last time and exit the loop. To provide this condition, we just need to get the current number using a getFromArray. Connect it to our last node, and set the second number to 8. This way, when the number is less than 8, the output would be true, otherwise false. If we connect the output to looping condition, we see that it breaks from the loop once the number isn't less than 8 anymore. Those are the basics of auto looping, for each, iterate, and do while constructs. Now let's see how to apply them to create colors, displacement, and animation. Here are the steps for creating this animation. First, we scatter some points, which will be used as the seeds for driving the changes in colors and displacement. Then, for each mesh vertex, we find the seeds within a radius around it, and we iterate over these seeds to get the distance between each seed and the mesh vertex. And we calculate the weight based on these distances, which will be used for generating the colors and displacement. And our final step is to animate the seeds, which will drive the movement of those circles. Here I have a mesh plane. I'm going to get a pass node so that I can easily switch to other mesh geometries later. Let's get a scatter points. Set the scatter mode to blue noise and the mount mode to radius. Get a value node so that we can adjust the number of points. And we can use a combination of point scope and terminal to visualize the points. These points will be the seeds for the following steps. Now for each mesh vertex, instead of calculating the distance to every seed, we can make the graph run faster by only looking at the seeds within a radius around it. And we can use the node getPointsInRadius to locate these seeds for every vertex. Connect the scattered points to geometry, and let's use a getPointPosition to get the positions of all the mesh vertices. Connect it to positions. Let's set the radius to 5 now. We can adjust it later. The outputs here are nested arrays. For example, here's what the output point indices look like. For each mesh vertex, the node finds the seeds within the given radius and put their indices in an array. If we iterate over these two arrays, we get access to each vertex and the indices of the seeds around it. Let's get a for each. Connect the mesh vertex positions and the seed indices to it. Go inside and make sure both are set to iteration targets. To calculate the distance between the seed and the mesh vertex, we also need the point positions of the seeds. So let's also connect these positions to the for each compound. Rename it to seed positions. And I'm going to rename these two as mesh vertex position and seed indices. Inside the loop, we need to do something so that for every vertex it assigns a weight, which we'll use to generate its color and displacement. If we just want to create a static geometry like these ones, it's most efficient to use the do-while compound. To be safe, I usually set the max iteration to be a number that's larger than the size of the input array, just in case I made a mistake which results in the condition being always true. This max iteration prevents me from getting trapped in an infinite loop. Here's how we generate the weight. We assign a radius to each seed. To simplify it, I'm going to use the same radius for all the seeds. You can use various radii if you want. For each vertex, we assign it with an initial weight of 1. Then we iterate through the seeds around it. If it's within the radius of the seed, we get the ratio of distance over radius. Replace the initial weight with this ratio and exit the loop. This way, if the mesh vertex is outside of any circle, it will have a weight of 1. If it's within the circle, it will have a weight between 0 and 1. Let's see how to program it. First, let's use a getFromArray to retrieve the seeds around each vertex. Connect the seed positions to array and seed indices to index. This outputs an array of the positions of the seeds. Now connect the seed positions and the mesh vertex position to the do-while and provide a radius for the seeds and an initial weight of 1 for the mesh vertex. We want to set the weight as a port state because we need to update it if the vertex is within a circle. Here for each iteration, we get the seed position using a getFromArray. Subtract from it the vertex position and the length of this vector is the distance between the 2 points. Then we get an if node. If the distance is greater than the radius, which means it's outside of the circle, we keep its original weight. If it's smaller than the radius, we calculate the ratio of the distance over the radius and use this ratio as the weight. Connect this Boolean value to looping condition so that once a vertex is found to be within the circle, it updates the weight and exits the loop. Go outside the loop connect the weight to the output of the for each compound. This completes the for each loop so that it calculates the weight for each mesh vertex in parallel. Go outside of the for each, and here the output is an array of the weights for all the mesh vertices. Now we can assign colors using a combination of evaluate F-curve and lerp. Connect two colors to first and second. This way a vertex with a weight of 0 will get the first color, and that with a weight of 1 will get the second color. Anything in between will be interpolated. To assign colors to mesh vertices, we can use the node setGeoProperty. Enter color for the property, connect the mesh plane to geometry, and the interpolated colors to data. Connect it to the output, and we see the colors. We can adjust the F-curve to change the gradient. To move the mesh vertices, we use a displace points. Instead of using the same weights as the colors, I'm going to get a change range to modify the scale. Let's get the array bounds of the values from the evaluate F-curve. And change the range to, say, 0 to 0.6. Connect the out points to the output, and we get this color mesh with deformations. We can change the amount of the seeds and the shape of the F-curve to modify its appearance. We can also easily change the initial geometry to apply the effects to all kinds of shapes. Now let's see how we create a more dynamic scene. The current setup would have problems when interactions between circles occur. For instance, here we see these edges. This is because the weight is calculated from one seed only. To get smooth transitions in the overlapping areas, we need to consider a combined influence from all the seeds within the radius. One way of quantifying this combined influence is to calculate a weighted distance. This is a formula for calculating the weighted distance. For every seed, we calculate a weight based on its distance to the mesh vertex. Get the sum of weight times distance and divide it by the sum of weight. You don't need to worry about how exactly this weight is calculated. I provided the formula as a compound. What we need to do is constructing a loop using iterate, starting with 0 for both the sum of the weights and sum of weight times distance. And for each iteration, add the weight of the current seed to the sum of the weight, and its weight times distance value to the sum of weight times distance. Let's go inside the for each loop. Get an iterate compound, delete the max iteration, connect the seed positions to it, and make sure it's set as the iteration target. Connect the mesh vertex to it, and get two value nodes of 0, one for the sum of the weight, the other the sum of weight times distance. We want to set both the wait and wait time distance as port states that update over the entire loop. Here's the compound for calculating the weight of the seed. Plug in the seed position and the mesh vertex position, and it outputs both the weight and wait times distance. We just need to get an add node, add the weight to the sum of the weight, and another add node, add the weight times distance value to the sum of weight times distance. Connect the results to the output, and we get the two sums that we need. Outside of the iterate, divide the sum of weight times distance by the sum of the weight, and we get the weighted distance. Just to be safe, in case no seed is found near the vertex, we skip this calculation and assign a positive value as the weighted distance so that we wouldn't have an error of 0 being the denominator. For that, I'm going to get an if. Get the array size of the seed positions. If it's 0, assign a weight of, say, 3 as the weighted distance. Otherwise, use the calculated value. Connect the result to the output, and we get the weighted distances for all the vertices. Go outside of for each. Let's change the value range to 0 and 1. And connect the result to evaluate F-curve. Now we see that the overlapping regions have smooth colors and displacements. To animate the seeds, I created this compound, which uses a fractal turbulence field to drive the movement of the seeds. It takes the initial seed positions and outputs new positions for every frame. Inside the compound, I set the port feedback of the positions to be the out positions. Here, the port feedback is similar to the port state in an iterate compound. At each frame, it samples the field at the current seed positions, and those vectors are added to the current positions to generate the updated positions. And the updated positions will be used as the input positions for the next frame. Connect the output to seed positions. Get a construct points. And connect the points to the port geometry of the get points in radius node. And we get the animated scene. We can make it look smoother by increasing this smoothness parameter of the weight distance compound, or by increasing the radius of influence. Connect the animated seeds to point scope, and we can visualize the moving seeds as well. We can play with the parameters such as colors and F-curve to alter the look of it. That's it for today. I understand that constructing loops can be frustrating if you're new to iterations, and it takes practice to get comfortable with it. Let me know in the comment if you have any question. Thanks for watching. Stay tuned, and I'll see you next time.